Let's look at example 1, page 413, section 5.5. Find the indefinite integral of x cubed cosine x to the fourth plus 2 using u substitution. Let me emphasize that u substitution, that technique will not work on every function, okay? You'll learn a whole lot. We're developing a toolkit for anti-differentiation, and this is our first technique that we're learning, our first tool. In Calculus 2, you'll learn other tools. For example, you'll learn integration by parts, that technique, and that undoes product rule. Right now, we're learning u substitution that undoes chain rule, okay? Now, the good thing is, if they give you a problem right now and it says u substitution, then that tool will work. In other words, chain rule was used to differentiate, and to undo it, then u substitution is your right tool. You know, later on in Cal 2, you'll have to decide what technique do I use. Here, they're telling us the technique. And we're really only going to learn one technique, because this is where Cal 1 stops. No, we're not finished with the material. We've got to go back. After we get really good at u substitution, we've got to go back and do 5.1, 5.2, 5.3, which is on definite integration, which means something different. Okay, this is indefinite integration. Okay, I let u be the inside function. Okay, if I've used chain rule, I've got a composite function. I've got an outside and inside. Okay, I let u be the inside function. So I let u be x to the fourth plus 2. The differential of u, you always take the differential. Remember, the differential is the derivative times the differential of the independent variable. And again, what's a differential? A differential of a dependent variable is just a derivative times the differential of the independent variable. It's just, think of it as just pushing symbols and it works, okay? But this is language that allows us to facilitate this procedure. Differentials actually are good for something else, and if you look in your table of contents at differentials in Chapter 4, you could do that section and see what they're actually good for in a way that'll make them make more sense, rather than this just symbol pushing sense. Okay? But we're learning a tool that works. All right, now I want to transform this into an integral that I know the answer for, that's in my chart in section 5.4. And the way I do that is I use this substitution. Now, I'm old and gray, and I've learned if I put the composite function first, that usually makes life easier. So if I put this composite function first, it usually makes life easier. So I'm going to do that. Cosine x to the fourth plus 2 is just what? U. Now what's left? X cubed dx. I look up here at my du, and I look for x cubed dx. There it is. So what do you think x cubed dx is equal to? What do you think? Divide both sides of this equation, du equal 4x cubed dx, by 4, and you get x cubed dx is du over 4. Do you see that? I'm going to write that up here. Du is 4x cubed dx, so du over 4 is x cubed dx. So I'm going to take x cubed dx and replace it with du over 4. Now, you never want to mix x's and u's ever. Okay? Isn't this simpler looking than what I started out with? And in fact, I can make it even more simple looking by bringing the 1/4 out front. Now, this is in my table in section 5.4. Antiderivative of cosine u is what? What do you differentiate to get cosine u? It's just sine u, isn't it? Remember, add my constant. Now, always put your answer in terms of your original variables. X to the 4th plus 2. This is my answer, I think, but it's always good to check. How can I check? Take the derivative of what I think is my antiderivative and see if I don't get the original integrand. 1/4 comes out front. Derivative of sine is cosine. But I got to multiply by the derivative of the inside. Derivative of c is 0. One-fourth times 4 is just 1. I've got x cubed times cosine x to the 4th plus 2. And lo and behold, that was my original integrand.